Comment je fais pour l'agrandir là?
Comment? Ah non, c'est parce que
Ouais. Okay. But yeah, if you don't already have a mesh, we'll have to make it. And so what we'll also discuss is how to optimize the mesh and how to profile WaveWatch to see how you can improve the mesh, or also that can be also interesting for looking at the source terms and where is the cost of the model. And we'll do some editing with some tools. And yeah, and the next step will be to actually design the contour and we'll build the mesh for that. So right now we'll just assume we have the right polygons to make the mesh. So again, it's all in Aaron's thesis and blah blah blah. All right. So imagine you have your mesh, you're running WaveWatch, and it's very slow, and you want to know why. So first thing you can do is to first recompile the code, not in with MPI, but make sure it's running for sequential. So that's using the SHRD switch and not the dist MPI switch. And then to be able to profile the code, you need to compile with the -d and -vd options. And they used to be default in the debug comp and link, but we need to put them back because somebody has commented them. Yeah. The -g, -pd, no, at some point there was in the comp and link. I don't know what happened. I think now they're commented, so you need to. No, not just BandLab, but default also. So it would be nice that it's uncommented, so that by default we can do that. Just minor comments. Huh? And so what is debugging? in the comp and link debug and the comp new debug and link new debug, it would be nice to put them back. And so if you compile with these options, then there will be some special output file coming out of the executable when you run it. And a special output file is daemon.out. And this daemon is for monitoring the performance of the code, and then you can use the tool dprof, which is usually installed on any Linux distribution. And if you just run, instead of running W3 shell by itself, you run dprof W3 shell. So that will run the code, and it will give you some extra output, which gives you this. And for example, so you can tell here in my case, what the amount of time taken by each of the routines of the model. And so they're ranked by the top to bottom. So the most of the cost of the model in that case, or 22% of the cost of the model here, is taken by this nice subroutine called W3XYPFSN2, which is the advection scheme for the N scheme. And this is part of the POF-SMD module. The second biggest item on the cost here is about the same, and this is my crazy dissipation parameterization with ST4. And then if you go back to ST3, this will be down to a few percent. So the ST4, which is contained this module, and the dissipation term is W3SDS4. It is a bit expensive. I think it's still not expensive enough, but yeah. The next one, which used to be the most expensive in all wave models, is nonlinear interactions, the DIA. This is this W3SNL1, which is part of the SNL1 module. And also, if you want to have some fun and try SNL2, then you'll see that then at that time with SNL2, it's going to be 99% of the cost will be SNL2. And this is the input. This is the advection. This is the advection for the refraction, I think. It's only 4%. And so based on this table, you can say, okay, well, if really this line, this advection scheme is taking a lot of the cost, then it's worth trying to reduce this. If it's down to 20, 30%, then maybe it's not a big deal to make some effort, and maybe your grade is good enough. All right, so that was another case. Yeah, before I tuned my grid and before I adjusted it, the cost of my advection scheme was 50% of the model. So 48% here. This was the case also for the Mediterranean, maybe. We had a slightly different parameterization, so it was a bit cheaper. So this is when you change the options in name lists. Again, this is still ST4, but you make ST4 cheaper and still pretty accurate. So you can play with the manual and go from test 451 options for ST4 to the test 441 or 5, and this is just by changing the name lists. Because some of the options, some of the pieces of ST4 are expensive. It's not everything which is expensive. Especially there's some loop to compute some spectral saturation parameters. And here, oh yeah, there's also the shoreline reflection here, was taking 1% of the code and all that stuff. And you can see also there's this power F is actually some, when you take some number to a power, right, like the direction to the power 2, if by some stupid reason, instead of taking power 2, you make it power some number, which is a real number, then you can use a different routine to compute the power, which is much more costly than just taking the square. So if you have something which is just a square in your code, it's just better to have it a square, not the power of some other variable. It's just another, and the exponentials and cosines, you can see them showing up. So this is one of the reasons why in WaveWatch all the cosines are pre-computed. So cosine of direction is a pre-computed table. You don't want to compute the cosine every time you do. All right. So so here we had a grid with a very big cost for the advection. So probably we can reduce that. And so the question is what defines time step on this mesh? So for regular grid, it's very simple. We have the TFL condition. And the TFL condition for regular grid is just the velocity times the time step divided by the spatial step. All right. And if the TFL is equal to 1, it means that your information in your grid is making one jump over one cell in one time step. And in that case, the time step is dx divided by the velocity. Now, for the triangle, the analogy of this is a dt instead of being just a dx is the area, because you're looking at the fluxes inside of the volume. So it's the area of the of that region divided by the sum of the velocities times the lengths around this volume. So that's the analog for a triangle mesh compared to the real mesh. Which means that your to change the DTX, you can try to have CFL equal 1 to have this. You can try to increase the area of your cell, or you can try to reduce the length. And of course, you will very easily see that if you want to maximize the ratio of area divided by length, it's better to have an element which is almost a square or a circle, right? Because if it's very flat, you're going to have a very long length and a very small area. So that already tells you that the flat triangle is not very good for the time steps. And also something which is maybe not so obvious at the beginning is that if you have this configuration and okay, you have a time step for this point, you may want to move this point and time step at that point. That will not work because the area of that cell is independent of the position of the point. It's because the area of that cell is actually only a function of this area of this big hexagon and not where the point is. You can do the maths, you'll see that. So if you just move this point number j, the time step at j will not change. So what you need to do is to move the neighbors, okay? Okay, there was some special stuff on the boundary. Yeah, so on the boundary, we rewrite, we overwrite the result with the forcing of the boundary. We actually don't need to take care of the shape of the triangles at the boundary. And this was 16 version 4.12. And yes, and for we have one time step for each spectral component. So each frequency in each direction has a different time step, and these time steps for each of these is defined as a minimum of all the time steps for the entire grid. And so in practice, the time step used by the code can be very small if there is only one small or flat triangle. And well, if it's small and flat in shallow water with a slow speed, it's not a big deal because the waves are slow, so the TFL does not go up. But if it's in deep water, yeah, that you have a small triangle, then it's more of a problem. So this is an example with my Hawaii mesh, and we'll be using that this afternoon. So this is a zoom on the mesh. You have the triangles here, and the worst guy in my mesh is this one with the blue symbol here, and it happens to be in the middle of this diamond-shaped pattern. So this triangle has 4 neighbors, and some meshing programs forbid to have this kind of configuration. And people that do tidal modeling know that this will also give instability. So usually, Florent Liard, for example, removes these nodes from his meshes. And so what I did in WaveWatch is, because these tend also to give very small time steps, I have a special tool to clean up these points with 4 neighbors. So this you have issue with these 4 neighbor nodes. You can have also issue with 2 neighbor nodes that can happen on the boundary. Same thing with 3 neighbors only. And in these cases, it's very easy to adjust the mesh locally, because what you do, you take these points with the 4 neighbors, you remove the points, and you just say that instead of having 4 triangles, you only have 2. You just split it in 2. You have 2 triangles, and that's it. You don't have to change all the mesh. It's only a local change in the mesh. So we will play with that, and then if you can really kind of do this kind of 4 neighbor business, then what you can do is actually to move the nodes around to maximize the time step. And again, you move the nodes around, not the neighbors, not the nodes themselves. So that's pretty much it, the TSL business. And yes, and so the next lecture, and I'll just really just continuation of that one. Yes, I'm going to do that. It's about how to do that in practice. Any questions? No. Which one is it? Maybe Polina? Which one? Oh. No, Sean, c'est pas ça. And this one, what is it? Oh, you know, this one I already talked about yesterday. So yeah, so let's just do the polymesh, because yeah, I think I had another set of slides, but it's really how to use a tool. So we'll just do it during the tutorial. Yeah. So yeah, so I'm done with this optimization, and then I'll discuss now how to. Any questions about these time steps, triangles? Okay, so obviously it was clear enough. Yeah. It really depends what you want. If you want to know the wave all along the islands, you use all the islands. If you don't care about the waves on the islands, it's just blocking for you, then use the regular gradient obstructions. But, we don't do obstructions with the triangle mesh. So it's in that case, yeah, we pretty much resolve all the islands we can, and of course there's then some small islands that we give it up or just merge them together. Like in our Iroise mesh, we do have the tas de poids, which can we see that from here? No, they're behind, right? So there's just a few rocks that stick out of the water. It's 50 meters across, and yeah. So instead of having just 3 rocks, I just make 1 triangle of 3 rocks. But yeah. So to create, so I showed you how to edit the mesh once we have it, but first to create the mesh, and this was also what we do this afternoon. What we will be using here is this tool called Polymesh, which is developed by Aaron Roland. There are other tools that exist, so you know they have their benefits and some drawbacks, but you can try something else. The Polymesh is an interface for a tool which a software to use in all these programs. Usually is called Triangle, which is a library to make triangle meshes. What Polymesh does is to define the criteria that set the shape of the triangles and to read the symmetry and do some interpolation and all that. And so Polymesh does that, interpolating bathymetric data, modifying the refinement conditions, how fine you want the triangles or not. You can define some special structures that the triangles have to follow, like the a river. You want to align. In most cases, you usually want to align the triangles with the river flow to avoid numerical diffusion. And there's also sorting of nodes to make the model faster, and it's sorted so that the number of the nodes tend to be, well, neighbor nodes tend to have numbers that are close to one another. And this makes it the code more efficient, because when you actually read data in memory, what's happening is it goes through the cache, and the cache in the memory, not the cache, not the money, it's the cache of the memory, contains usually not just one value, but some values around it. And so if you already had the values in the cache stored, it makes the whole thing faster. So this is the reason for sorting the nodes in the grid. So the input files that we typically need the some boundary polygon, some island polygon. We can use some extra polygon to define the refinements, and a bathymetry database, which is just a big text file with latitude, longitude, latitude, and depth, 3 columns text. So this is what it looks like, the bathymetry file with the XYZ. You just need to have the first line, the number of nodes, and you can have 100 million nodes that be able to work. So I don't know it's how it's going for the ULC with your UXYZ, but Guillaume is working on this new mesh. So as its name says, Polymesh work with polygons to define pretty much everything. And they look like that. So you have some comment line, in which you can put some name of the polygon if you want, and then the list of the points of the polygon with, again, X, Y, and Z. So this is the case with stuff in meters. You can do in latitude and longitude. And for some things, you don't need to specify the depths. For example, you have the shoreline, you can just put 0 if you want. And so the file contains polygons like that. Each polygon finishes with a -1 line. And that's it. So this is an example. One of the test cases that goes with WaveWorks is the TP 2.7 maybe. It's the Limon Harbor in Costa Rica. There's an island in front, and it's a harbor jetty. And no, this is a mesh you can do. If you change the criteria, you can make a smaller mesh, just one number to change. You can refine the mesh in some regions like this. You can create some structures and make the triangles to follow the structures you want for some reason. So that's useful for rivers in particular, to have the triangles that follow the line of the river. And yeah, so here it uses some funny depths on these things, and here you get the depth map. You can have the depth, the resolution adjusted with the depths. We'll do that, and ooh, that was it. Okay, I thought there was more details, but all right. So that's a basic principle of Polymesh. There is a manual for Polymesh, and yeah, it's actually easier to do when you actually do the tutorial. So that's nothing really special to it. One thing which was not said here is that on top of the data that you have to give, there's also an input file which defines all the settings, the criteria, how you use the depth or not, and we will edit these input files and the bathymetry data. So that's just the principle of the Polymesh. I'm sure the manual and everything is on your. It's going to be in the tutorials and all that.